We are ready now to embark on our study of Newtonian mechanics. One small preliminary, a special case of what we have already looked at a little earlier would be appropriate, and this has to do with motion in a circle and what the acceleration required to maintain such a motion is. And we will come back to this topic a little later, but I thought I should mention it at this juncture because it gives you a good instance of how the unit vectors in coordinate systems other than Cartesian coordinates are useful in description of motion. So we have in mind, I am going to look at this topic, we have in mind a particle which is moving in the xy plane, this is the origin, in a circle. And we do not say anything more about the motion at the moment, such as what is the force causing this motion or anything of that kind. We observe that it is moving in a circle, it is restricted to a path which lies on this circle and moves in a circle with some angular speed of some kind, and then the question is, how does one describe the kinematics of this particle? Well, as usual, and let us draw a slightly better figure than this. The radial distance in the xy plane from the origin to this point is some rho, and this vector rho is the position vector of the particle at some instant of time t. The radial unit vector E sub rho is in this direction, and the tangential vector E sub phi, which increases direction of increasing azimuthal angle phi, is normal to E sub rho and points in that direction at this point, and of course these two vectors change direction as you move, as the particle moves along the circle. Now the starting point is to say that the position vector of this particle at any time is equal to rho times E sub rho, and remembering that rho is a constant in this case, it immediately tells us that since the radius of this circle is prescribed to you, this is equal to r times E sub rho. Therefore, any change in this position vector rho comes entirely from the change in the unit vector in the radial direction, and let us call that a function of t. So we have rho of t equal to r times E rho as a function of t. Therefore, the velocity of the particle v, which by definition is the rate of change of its position vector over dt, that is the definition of the velocity, instantaneous velocity. This must be equal to r times d over dt of E rho of t. So notice that we have the time derivative of a unit vector which is constant in magnitude, unit magnitude, but whose direction is changing as a function of time in some fashion or the other, which depends on the force on this particle. But at the moment we are interested in evaluating this d over dt E rho of t, and we can do that in many ways. One of them is to say that E rho at any instant of time t, so let me put the t in, we know is equal to cosine of phi, which is a function of time, times Ex, and no argument of t or anything like that here because that is a constant vector, plus sine phi, which is a function of t, times Ey. Therefore, the derivative of E rho comes from the derivative of cos phi with respect to time and sine phi with respect to time. So that would be a standard way of doing this, but we can write the answer down more easily by just the geometry of it, and let us draw another figure to see how this works. A slightly magnified figure. So here is the circle. At some instant of time this is rho and the radius vector points in this direction, so this is E rho of t, and at a later instant of time, infinitesimally later instant of time, t plus delta t, and I am drawing this in an exaggerated way so that you begin to see what is going on. This thing here is E rho at a later instant of time, t plus delta t, since the particle is moving in this direction counterclockwise, and you can see this vector is not parallel to this vector, so it is changed in direction. And what we need to do to find the change in the vector is to translate this vector parallel translate it here. So make it parallel to its original, make it parallel to itself and bring it to this point here, and since this angle is phi and that angle is delta phi, the incremental increase in phi, by the law of corresponding angles, this angle is also equal to delta phi. And each of these vectors has unit magnitude. Now if I draw this figure in a little exaggerated way, things become clear. So you have unit magnitude E rho at time t, you have an angle delta phi between the two, that is this angle, another unit magnitude 1 here, and this is E rho at t plus delta t, and it is quite clear by the addition of vectors that this vector here pointing this direction is the difference between E rho at t plus delta t and E rho at time t. So this vector here is E rho at time t plus delta t minus E rho at time t, because E rho at time t plus this difference is equal to E rho at t plus delta t by the triangle rule for the addition of vectors. So once we have that in place, this quantity is equal to, it is equal to the length of this arc or this vector, infinitesimal vector, which is equal to what? There is an angle delta phi and there is a base or radius 1. So it is clear that the magnitude of this vector arc divided by the radius is equal to delta phi, therefore arc is equal to delta phi multiplied by 1. Okay. So this is equal to delta phi times the vector in this direction normal to E rho. If it is infinitesimal delta t, then this vector becomes essentially normal to E rho, and that is the direction of E phi, as you can see it is normal to it in this direction. So it is delta phi times E phi of t, and therefore if you divide both sides by delta t and take the limit, d E rho at time t over dt is therefore limit delta t goes to 0, E rho at time t plus delta t minus E rho at time t divided by delta t. The numerator is a vector, the difference of two unit vectors, and that turned out to be this quantity here, and therefore this is equal to limit, let me write this out explicitly, delta t goes to 0, delta phi of t over delta t multiplied by E phi of t. So this tells us that the velocity v at time t, which was equal to r times d E rho t over dt, is equal to r times the limit of this quantity, which is the angular speed. It is the rate of change of the azimuthal angle, it is phi dot of t or d phi over dt. So d phi of t over dt times E phi of t, which is the same as saying this is equal to r times omega times E phi of t, where omega stands for the angular speed. Of course, we could have derived this more simply by writing E rho in Cartesian coordinates and noticing that the derivative of E rho of t would be just E phi of t times whatever this quantity is, d phi over dt. Okay. We could have done it that way, but this geometrical illustration makes it very clear. Notice that this is independent of whether omega is constant in time or not. So we are not restricting ourselves to uniform circular motion. You have motion in a circle, but the particle could be accelerating, the angular acceleration could be non-zero along the circumference of the circle. So this is not restricted to uniform circular motion, it is a general relation. V of t is always tangential. That is obvious because when you move in a circle, it is clear that the instantaneous velocity is always tangential to the path of the particle. So again, there is the path of the particle, and at any instant of time the instantaneous velocity is tangential along E phi at any instant of time. That is indeed what has happened, and the magnitude is proportional to r omega. So we have our important result which says that the speed which could depend on time is equal to r times omega of t in general. So for circular motion, uniform or otherwise, the speed is the radius of the circle multiplied by the angular speed out here. I emphasize again that this is independent of whether omega is a constant or not. Even if the angular acceleration is not 0, it is still true. This relation is still true. It is a purely geometrical relation here. So we have our first result which says what the velocity is in terms of the tangential vector and the angular speed here. The next thing to do is to ask for the acceleration, and there we need now to differentiate these quantities. So it says the acceleration a of t, this is the acceleration, instantaneous acceleration is again by definition dv t over dt, and we need to differentiate this combination here, but notice that capital R is a constant, so that does not get differentiated, and by the chain rule this is therefore d omega over dt, that could possibly be a function of time, times E phi of t plus r omega times d E phi t over dt. So there are two components to it, one of them coming from the fact that the angular speed might be time dependent and therefore there might be an angular acceleration, and the other coming from the fact that this vector E phi of t changes in direction as the particle moves along the circle. So there is an instantaneous acceleration due to the change in direction of this tangential vector, the unit tangent vector here, and we need to compute that quantity. As before, same argument as before, one could write down explicitly E phi of t is equal to minus sin phi times Ex plus cos phi times Ey, and differentiating this, remembering that Ex and Ey are constants, the only thing that gets differentiated is this and that. This immediately tells you this is equal to minus cos phi Ex plus sin phi Ey, which is simply E rho. So this immediately says this is equal to E rho multiply as a function of time multiplied by d phi over dt or phi dot. So when we differentiate sin phi with respect to time, first you get cos phi and then d phi over dt, because phi is a function of t. So we put that in there, and this immediately tells you that you have two terms here. This is equal to r times d omega t over dt E phi of t, and there was a minus sign here, so this is equal to minus r omega squared, because there is another omega from this quantity is omega, times E rho of t. So that is our final answer for the acceleration, general acceleration of a particle moving in a circular path. The general expression has two terms, one of them coming from the possibility that as it moves along the circle, the angular speed might change as a function of time. It might accelerate, it might decelerate, and so on, and that gives you a contribution here which is purely tangential. But, and here is the crucial point, in order to even maintain this particle on a circle, you have to have a centripetal acceleration directed towards the origin. This has a minus sign, these are positive quantities, so this is directed towards the center of the circle. In other words, if a particle moves in a circular path, uniformly or otherwise, there has to be a centripetal force which pushes it towards the center of the circle constantly, incessantly, otherwise it will not move in a circle. Now the physical origin of this acceleration must come from Newton's laws. We must know from Newton's laws, which says the mass is equal to, times the acceleration is the force. To maintain this acceleration you need a force, and that force has to have a component which is directed inwards, otherwise you cannot have circular motion no matter what. So I emphasize again, this portion, if you like, is the tangential acceleration, and this portion with the minus sign is the radial acceleration or the centripetal acceleration. This thing is also called the centripetal because it is towards the center. Okay. And it exists always. Even if omega is a constant, it still exists. Now a little paradox here. So this is immediately telling you something which is a little counterintuitive. To keep an object moving in a circle, you need to have a force that directed towards the center at all times. You might also have a force that is tangential, which will then cause a change in the angular speed. But even to maintain it at constant angular speed, you need a force directed towards the center. Now what does that, where does that force come from in the case of planets moving around the sun? If the orbit is approximately circular, it comes of course from the force of gravity which the sun exerts on the planets. So there is a centripetal force which pulls the object inwards. What happens when you twirl a stone round in a circle tied to a string, another end to one end of a string? Well, the tension in the string is providing the centripetal force in this case. Here is a little paradox. Imagine having a train moving in a circular track in this fashion. At any time, here is the train, it is clear that the engine is pulling it in a tangential direction. How then does this train move in a circular track? Because it should really be moving along this tangent in a straight line, but it moves in a curved path. There has to be a force on the train which is directed towards the center at all times. So when the train is here, there's engines pulling like that, but there has to be a force which is directed inwards in this direction. I leave it to you to figure out where the normal force, where the force that is radially inwards on the train comes from. Even though the engine appears to be pulling it in a straight along it, the length of the train, you still have a force, have to have a force inwards, otherwise it would not be possible to maintain this train on a circular path. So I leave it to you to figure out where this comes from. Now you will also notice that these formulas are special cases of the general expression we wrote down for the acceleration in plane polar coordinates, where there were components which came from the fact that the radius itself could change, the radial distance itself could change. So there was a term which depended on rho double dot, the second derivative of rho, the radial acceleration. There was another term which depended on rho dot and a combination of rho dot and phi dot and so on. But this is what happens if I set rho equal to r, a constant. This is a special case of the more general formula for motion in a plane in plane polar coordinates that we derived earlier, the expression for the acceleration that had several terms, and some of them disappear when rho is a constant, as in this case here. We will return to this problem of motion in a circle and talk about non-inertial forces, pseudo forces, a little later. But now I am going to go back to our main task, which is to embark upon the study of dynamics. We are going to have a lot to say about this, about Newton's laws. So let me. Okay. As you know, there are three basic laws of motion propounded by Newton. The first of them is the law of inertia, which is actually known to Galileo himself, and it essentially says that objects of suitable size, not too small, no quantum mechanics, not too fast, no relativity, such objects move in such a manner as to satisfy Newton's equations of motion. These three equations of motion are believed to encompass all of the dynamics that we need to know for Newton's in the regime in which these laws are applicable. The first law says that an object will continue to be at rest or in a state of uniform motion in a straight line if there is unless acted upon by an external force. So it is saying something about inertia. So the first law is essentially a statement of what an inertial frame is in this sense. It is a frame in which the first law is valid. So if you roll a marble on a floor and you discover that it is essentially frictionless, moves on forever, in the assumption that there is no friction, if it moves in a straight line forever, then we know that the floor is part of an inertial frame of reference. Okay. The second law is where the meat is, this is where the dynamics is, but already in the first law certain assumptions have gone in. For instance, it has been assumed that space is infinite in extent and has a Euclidean structure. It is 3-dimensional Euclidean space. It has also been assumed that time flows inexorably. There is something called absolute time flowing inexorably from the infinite past to the infinite future. Now these are assumptions which are not really valid. We have discovered since then that these have to be taken with some qualifications and their approximations. But in Newtonian mechanics, the first law has already presumed that these concepts have been taken and have been incorporated. That it has been presumed that time is an absolute quantity which is flowing from the past to the future at a uniform rate, and that space is of infinite dimension, infinite extent, and is Euclidean in structure. Okay. The second law says something about the way a system responds to an external force. So in some sense it is the very definition of force, if you like. What it says is that the mass times the acceleration. So here is the second law. It says the mass times the acceleration of a body is equal to the force applied on this body, the instantaneous force applied on this body. So let us encompass that by saying, let us say this is V of t is F of t. It does not say anything about where this force comes from, what are the other bodies that act on this object in order to produce a force on it. It does not say, it says it does not care. It says the moment there is a force on the body reacts by accelerating, not changing its position immediately but changing its velocity. The force is proportional to the acceleration and not the displacement. The force is not proportional directly to the velocity. This is very important. It says a force causes a change in the velocity and the rate of that change is dV over dt. This quantity here, the acceleration, is multiplied by a certain constant property of this object called its mass. The way one should really look at this is to say, if you apply a force on a body, then the response of the body is by an acceleration, and the acceleration is proportional to the force, and the constant of proportionality is 1 over the mass of this body. So in that sense this is a response stimulus relationship here. It has got many other interesting properties, some of which we will talk about. For instance, we have written a vector equation and I do not specify what the coordinate system is, and the answer, as we said right in the beginning, is that it does not matter what coordinate system you are in, because this is a vector equation and we know how these quantities transform under rotations and translations of the coordinate axis. So if you have tilted coordinates with respect to your original coordinate frame somewhere else and it is shifted somewhere else in space, it does not matter. This relation is still true in form. In other words, in the new frame you get m dv prime over dt is f prime of t, and you are still guaranteed the same proportionality. So that is the essence of this vector law of motion, if you like, and this is the problem that basically one has to solve in dynamics. So notice also that it is linear in the sense that if I have two forces acting on a body, then the resultant acceleration is guaranteed to be the sum of the accelerations in a vector sense. So if for instance you have m times a1 for a force F1 on the body, and you have m times a2 for the force F2 on the body, you are guaranteed that if you have a force F equal to F1 plus F2, you have an acceleration A which is guaranteed to be equal to m times A1 plus A2. This looks like a trivial statement, but it is a profound statement. It says the response of this object, its acceleration, is linear in whatever is the stimulus, in whatever force is applied, independent of the nature of that force. So if you have one force which is mechanical, another force which is electrical on this body, and the first force produces an acceleration a1, the second produces an acceleration a2, you are guaranteed that when both forces act simultaneously on the body, the resultant acceleration is again the vector sum of the individual accelerations caused by the two individual forces. This is not at all obvious, but it is a straightforward consequence of Newton's law of motion, and it has very deep implications. It is a linear law in that sense. Had it been something else more complicated, like proportional to the third power of the force or something like that, we would have had very many more intricate effects going on, but we do not. We have a straightforward linear superposition in operation here in this second law. There are other consequences as well, and I will talk about some of them as we go along, but first let me say what is the basic problem. The basic problem of dynamics here, the fundamental problem is, for a single body for instance, once you are given an equation of this kind and you are told what this f of t is, the basic problem is to find out what is the velocity at any instant of time and what is the position of this particle at any instant of time. So that is the task, to solve this differential equation and discover what is the velocity and what is the position at any instant of time. Now in principle this is not such a formidable task, it looks fairly straightforward. For instance, I could take this equation and bring m to the right hand side, that is just a constant, and then if I integrate both sides by multiplying by dt, so you have dvt equal to 1 over m, which is a constant, and then a function of t dt on this side, and I integrate both sides from time 0 t equal to 0 up to some time t, and I integrate this side as well, t equal to 0 up to some time t. These are definite integrals from 0 to any given specified time t, so I need to use another symbol for the integration symbol, integration variable. So let us write it in this fashion. It is always a good idea to keep variables distinguished from each other. And then this quantity here is a total differential. So by definition this side, left hand side, is v of t minus v of 0. Notice this, you need to put in this term here, you need to tell me what is the initial velocity at some initial instant of time which you prescribe. That quantity is equal to 1 over m integral from 0 up to t f of t prime, that is a vector dt prime. I do not have to write t equal to 0 because it is an integral with respect to t itself, the time itself. Okay. I needed to do that here to tell you what I integrated over, what is the quantity I integrated over. So here is the formal solution to this equation, formal solution, because we do not really know what f of t on the right hand side is, and you will see where the complication comes in a minute, but this is the formal solution. And therefore if I write this out in terms of the velocity, it says v of t is equal to the rate of change of the position r of t, the position vector at any instant, that is the definition of the position vector. This quantity is equal to v of 0 plus 1 over m, an integral from 0 to t. Since we are going to have more than one integral, let me change the variable of integration. It does not matter what I call the variable of integration, it is only a label which will disappear after the integration. So let me call it t1 f of t1, and let us put the dt1 right away here in this fashion. This is a definite integral and it depends, the answer depends only on the end points. So whatever the value of this integral is, you have the indefinite integral is, you have to substitute for t1 the value t and subtract from it whatever you get by substituting the value 0 out here. So I emphasize again, t1 is a variable of integration, it is an index of summation if you like, and it should not appear in the final answer at all. So this is the formal solution to this differential equation here, but it still involves a differential, it still involves the rate of change of the position, and the next step should be to integrate that. And what would one get? Again I multiply by dt and integrate it, so drt, let me write it out, is v of 0 dt. This is a constant. This is a constant vector because it just says whatever happened to be the initial velocity at t equal to 0, that vector has to be put in there in place, and it is a constant vector, it does not change with time. Okay. So this is v of 0 times dt plus 1 over m, an integral from 0 to t dt1 f of t1. This whole thing is some function of t multiplied by t dt. But it is a vector function and we should never lose track of that. This quantity here is a vector function, and as you know, the elementary definition of the integral is like a summation. You break up this interval of integration into small infinitesimal pieces and add up all the little pieces that contribute, and here you got to do a vector addition here. So that is what is meant by saying an integral over a vector. Okay. So that is the formal expression for dr of t, and if I integrate it once again, then 0 to t dr of t, t equal to 0 up to t dr of t prime is equal to, on the right hand side you get v of 0, that is a constant vector, times 0 to t dt prime. So the first step is to call this t prime everywhere, t prime in that fashion, and then dt prime, and the next step is to say this is 1 over m, an integral from 0 up to t dt prime, integral from 0 up to t prime dt1 f of t1. And this is not such a trivial integral. This portion is trivial, it is just t. So I can get rid of this plus this quantity here. And what is the left hand side? The left hand side is r of t minus r of 0, and that is equal to this quantity on this side. Okay. And of course if I move the r of 0 to the right hand side, it is equal to this plus this, and that is the formal solution to the problem of integrating Newton's equation of motion for a particle or for a body of some kind, a single object. Okay. But this is not so simple as it looks, and now I will comment further on what this integral is and why it is so non-trivial to evaluate.